Good morning, class. So today we are going to discuss radical expressions. So next we have rationalizing the denominator. So it is the standard form. It is often useful to eliminate the radical in a denominator by multiplying both numerator and denominator by an appropriate expression. So this procedure is called rationalizing the denominator. If the denominator is of the form of square root of a, so we multiply numerator and denominator by square root of a. So in doing this, we multiply the given quantity by 1. So we do not change each value. So this is what we mean. 1 over the square root of a is equal to 1 over square root of a times 1. But this one can be written as square root of a over a. Take note, square root of a over square root of a is just equal to 1. So that we do not change the original given, which is now 1 over square root of a. Now, after rationalizing the denominator, we multiply numerator by numerator as well as the denominator by denominator. So the product now of the numerator is 1 times square root of a equals square root of a. Square root of a times square root of a is just equal to a because a times a is a squared and then square root of a squared is just equal to a. Again, you remember this one. If you are multiplying the same number, square root by square root of a certain number, then the answer is not the same number. Shall we say a? Square root of a times square root of a is just equal to a. Okay, rationalize the denominator of each fraction. So we have 4 square root of 2 times multiplying by square root of 2 over square root of 2. So multiplying that one, we have 4 square root of 2 over square root of 2 times square root of 2 is equal to 2. Because 2 times 2 is 4, but square root of 4 is 2. Okay? So for this case, for letter B, I will just do it directly. So multiply by its appropriate radical. We have here to multiply square root of 5 times square root of 5. Okay, so take note, our goal here is to rationalize the denominator. When we say rationalize, we are trying to eliminate the radical sign. So in this case, I multiply now the denominator of square root of 5 by square root of 5 itself, so that the product of the denominator will give you a whole number. Now, let's multiply. Square root of 7 times 5 is the square root of 35 over square root of 5 times square root of 5 is just 5. Okay? And for letter C, we have denominator is square root of 14. So what number are we going to rationalize the square root of 14 to make it perfect square? So we have 14. So 14 is not a perfect square. So what are we going to do for that? So we multiply also by square root of 14. Okay? So let's multiply this one by square root of 14 over square root of 14. So let's try to multiply. We have 7 times, what is 3 times 14? So we have square root of 42 over square root of 14 times square root of 14 is just equal to 14. So the numerator now will give us 7 times the square root of 42. But we have to think of the factors of 42 wherein one of the factors is a perfect square. Okay? So we cannot think of the square root of 42, right? So therefore, what are we going to do is that we just simplify the whole numbers, which is 7 and 14. So The coefficient of 7 and the denominator of 14, we can reduce to the lowest term. Therefore, the answer is by 7, this is now 1, and by 7, this is now 2. Therefore, the final answer is square root of 42 over 2. Okay, for letter D, we have 3 square root of 6 over square root of 18. So 18 is not a perfect square. So we are going to find a multiplier wherein the product of that becomes a perfect square. Shall we say square root of 2? So square root of 18 times square root of 2 equals 36. So therefore, 36 is a perfect square. So square root of 2 is correct. So therefore, I'm going to rationalize this one with the square root of 2. So multiply this by square root of 2 over square root of 2. So multiplying this one, we have now 3 times square root of 6 times 2 is 12 all over 8. Square root of 18 times square root of 2 is a square root of 36. But the denominator now is a perfect square because we rationalize the denominator, and that's our target, to make the denominator becomes a perfect square. So we have now 3 times factors of 12, we have 4 times 3, wherein 4 is a perfect square. So we will simplify that one later. And 36, square root of 36 is 6. So we can write now 3 times square root of 4 is 2, square root of 3 all over 6. And 3 times 2 equals 6, square root of 3 over 6. So we can cancel now the the whole number of 6 over 6. So therefore, the final answer is just the square root of 3. So we have the square root of 3 is the answer. Next, we have the idea of conjugate. So an expression with exactly two terms is called a binomial expression. Two binomial expressions whose first terms are equal and last terms are opposite are called conjugates. For example, we have x plus y. So x plus y and x minus y are conjugates. So the first and the last terms are the same, but we change only the sign from positive to negative or from negative to positive. So the conjugate of 3x minus 6 is 3x plus 6. So these two examples are also conjugates. So rationalize the denominator of each fraction. So since the denominator is binomial, so we're going to use the idea of multiplying by its conjugate. Now, the conjugate for this, we have to multiply this by square root of 3 minus 1 over square root of 3 minus 1. So multiply the numerator with the conjugate. We have now the square root of 3 minus 1 over, since the denominator looks like our previous topic of find the special products, which is now the product of sum and difference of two terms, whose product for that is the difference of two squares. So in doing that, we are just going to square the first term minus the square of the last term. So we apply our previous knowledge of special products. Now, we have square root of 3 minus 1 over the square of the square root of 3. This one and this one will be cancelled. So I have 3 minus 1 squared is 1. So simplifying further the denominator, so the denominator becomes 3 minus 1 is 2, and copy the numerator. We have square root of 3 minus 1 all over 2. And this is now the answer. All right, for letter B, so what is the conjugate of our denominator? This will now be multiplied by square root of 3 plus the square root of 2 all over the square root of 3 plus the square root of 2. Do not forget, our idea of multiplying the conjugate is we multiplied by 1 because the one that I write it here is equivalent to 1 when you're going to divide. Now, let's multiply numerator by numerator. So we can write now 2 times square root of 3 plus the square root of 2. All right, all over square of the first term, which is now the square of the square root of 3 minus the square of the square root of 2. So simplifying this, as you can see, I did not use distributive property for this, but I'm just showing that we are supposed to apply the distributive property. So I will just write as 1 as 2 times the square root of 3 minus the square root of 2 all over. This is now cancelled, cancelled. We have 3 minus, this is cancelled and cancelled. So we have now 2. Therefore, 3 minus 2 is 1. So a number divided by 1. So the answer now is just the numerator of 2 times square root of 3 minus the square root of 2. So I don't need to write here 1 because it's just 1. Okay? For letter C, okay, for letter C, I will solve it here because we are running out of space in that slide. So for this, our conjugate is 2 square root of 5 plus 3 square root of 2, our conjugate. Okay, so multiply this by 2 square root of 5 plus 3 square root of 2 all over 2 square root of 5 plus 3 square root of 2. So multiplying this, we can write now as square root of 5 plus 2 square root of 2 times 2 square root of 5 plus 3 square root of 2 all over. So apply the idea of the product of sum and difference of two terms, whose product is the square of the first term minus the square of the last term. So the first term is 2 square root of 5, so you square, minus the square of the last term. We have 3 square root of 2, then square of that. Okay? Now, to simplify further, we are in the numerator, we're going to use the FOIL method. So we can write now square root of 5 times 2 square root of 5 equals, we have 2 times 5. Because square root of 5 and square root of 5 is just 5. That's for the first term. And for the outer terms, we have square root of 5 times 3 square root of 2. So the product there becomes 3 square root of 10. This one, square root of 5 times 3 square root of 2. We have 3 square root of 10. And for the inner terms, we have square root of 2 times 2 square root of 5. So the product will becomes 2 square root of 10. And for the last terms, square root of 2 times 3 square root of 2, we have now plus 3 times 2. Because square root of 2 times square root of 2 is 2, and we have the coefficient of 3, therefore we have 3 times 2. All over, so the denominator is easier now. So the square of 2 square root of 2, the square of 2 is 4. And then the square of the square root of 5 is just 5 minus the same procedure using distributive property. 3 squared is 9 times the square of the square root of 2 is 2. So simplify again. Combining like terms in the numerator, we have now 2 times 5 is 10. So maybe I can write it here first. I have 10 plus, this one are like terms, so combine their coefficients. So 3 plus 2 is 5. So I can write 5 square root of 10. And this one is plus 6. 3 times 2 is 6. So this one now is 4 times 5 is 20 minus 9 times 2 is 18. Simplifying this further. So by combining like terms in the numerator, we have 10 plus 6, we have 16 plus 5 square root of 10. So square root of 10 is already in the simplest radical form because 10 has no factors that will give one of the factors is a perfect root. Okay, so since it doesn't have a perfect root if you're going to factor for 10, so therefore square root of 10 is the simplest radical form. All over 20 minus 18 is 2. So this is now the final answer. See, I cannot reduce this one anymore because 5 over 2 is not a whole number. Although 16 is divisible by 2, but because of this 5 is not divisible by 2, so I remain this answer. So the next number we are going to simplify x square root of x minus square root of x all over x minus square root of x. So the idea here is just the same, similar to the previous example, that we are going to rationalize the denominator by its conjugate. So I can write here now x square root of x minus the square root of x all over x minus square root of x. So the multiply by its conjugate, we have x plus the square root of x over x plus the square root of x. Now, multiplying this one, so we have, I will just write here x square root of x minus the square root of x times x plus the square root of x all over, we have the square of the first term minus the square of the last term is the square root of x. And then for the numerator, I'm going to use the FOIL method. So we have x square root of x times x. So we have x here as a coefficient and this is a whole number as well. Therefore, we have x times x is the x squared. So we have x squared square root of x. And then outer terms, x square root of x times square root of x, we have square root of x times square root of x is x. But we have a coefficient, therefore, x squared. So we have plus x squared. And then for the inner terms, we have square root of x times x. So the inner terms, we have minus x square root of x. And then for the last terms, negative square root of x times square root of x is just negative x. All over, we have the square of x squared is x squared minus the square of the square root of x is just x. So simplifying this, I will just write it here, square root of x and the square root of x here. So we can combine their coefficients. So we have x squared minus x. Quantity to that, we have square root of x. And then this is what I combine, the square root of x and this one because they are having the same radicand. So combining their coefficients, we have now x squared minus x times the square root of x. And then we have plus x squared minus x all over x squared minus x. Okay, so as you can see here in the numerator, so we have x squared minus x, and we also have x squared minus x. If we are going to group this one, I will use quantity for this. Then we can factor out, okay? Because this is the first term. Up to that, the quantity of x squared minus x times square root of x, that is now first term, plus the second term, which I group now, we have x squared minus x. So there is a common factor to that. So therefore, I can factor out now the quantity of x squared minus x, that's a common factor, and then divide this term, x squared minus x of square root of x divided by x squared minus x. So x squared minus x is cancelled, so the quotient is just square root of x. and then plus, this is now our second term, the one that I enclosed to parentheses. So x squared minus x divided by x squared minus x, which is the common factor. So the quotient will be equal to 1. So we therefore plus 1 all over x squared minus x. So what can you say about this? So x squared minus x and this can be cancelled. So we have now the final answer is we have the square root of x plus 1. So this is our answer. Okay, let's continue. So we have properties of nth roots. Number one, the nth root of AB can be written as the nth root of A times the nth root of B. Then number two, the nth root of A over B is equal to the nth root of A over the nth root of B. And number three, we have the m root of the nth root of A. So we are just going to multiply the two indices. So we have now the product of the mn root of A. Okay, I will emphasize this one using the example. If I have the square root of the cube root of 729. So first of all, multiply their indices. So the index here is 2 times 3. That is why you have there the 6th root of 729. And the 6th root of 729 is 3. And how did you solve for that? You multiply you will write that one as 3 to the power of 6. 3 to the power of 6 is 729. Okay? In other words, I'm rewriting this one. We have the 6th root of 729 can be written as the 6th root of 3 to the power of 6 because 3 to the power of 6 is 729. And then we can just cancel there the exponent and the index. Therefore, the answer is just equal to 3. And number 4, we have the nth root of a raised to n. As you can see here, the exponent and the index are the same. Therefore, it will be cancelled. So the answer is just a if n is odd. But for n is even, then the nth root of the a raised to n is the absolute value of a. For example, your n is 4. That's even, right? So the fourth root of the quantity of negative 3 raised to the power of 4. So cancel the 4, but the answer is the absolute value of negative 3. And take the absolute value of negative 3, so the answer is 5. So the other example, if n is odd, shall we say your index here, the n is odd, the cube root of the quantity of negative 5, the power of 3. So cancel the exponent and the index because they are just the same. So the answer there is negative 5, not the absolute value. Take note when the value of n is odd. But if n is even, take the absolute value. All right? So working with radical expressions, we can only multiply or divide radical expressions. We have the same index. However, we can try to make different indices equal by using the property of radical expressions. So I will show this one my solution. So in this case now, fourth root of a cubed times the square root of a. So their indices are different. The first one is whose index is 4 and the value of index here is 2. So they are different. So to solve for that, we're going to make the index be equal. So first of all, we're going to write the given in terms of fractional exponent. We have the fourth root of a to the third power can be written as a to the power of 3/4 times a to the power of 1/2. Now, since we have the same base, we can write a single form. So you can write now a, and then we are going to find the LCD of their exponents. So the exponents are 3/4 and 1/2. So the LCD between 4 and 2 is 4. Okay, and then the LCD now divided by the denominator, 4 divided by 4 is 1 times the numerator is 3. So therefore the product is 3 plus, I will use plus because this is multiplication. So we apply the multiplication law of exponents. And then we have 4 divided by 2 is 2 times 1 is 2. Therefore, we can write now as a to the power of 5 over 4. Now, from fractional exponent, we can express now our answer in terms of radical form. And this is now equivalent to, we start first with the index. We have the fourth power of a raised to 5. Okay, so we are going to simplify this further. Since the exponent is greater than the value of n, then it can be simplified further. Or this can be written now as the fourth root of a raised to 4 times a. So therefore, we have the fourth root of a raised to 4 is just a. So we have a times the fourth root of a is the simplest form of the answer. Okay, so for letter B, in the numerator, we are going to use the same procedure with letter A. We have to rewrite first the given. So let's start first with a raised to 1/2 times a raised to 1/4 all over a raised to 1/3. Okay, but I can write this one as a single term, although the operation involved here is multiplication and division. So we can write here as a raised to, this numerator will be, will apply the multiplication law of exponents. So therefore, we add the exponents. So we have 1/2 plus 1/4. And since we have a denominator of a raised to 1/3, so in division law of exponent, we have to subtract their exponent. So minus 1/3. So we can write now a and then find the common LCD between 2, 4, and 3. So the LCD between 2, 4, and 3 is 12. So I can write 12. So that's the common index now, or common denominator. So 12 divided by 2 is 6 times 1. We have 6 plus 12 divided by 4 is 3 times 1 is 3 minus. So 12 divided by 3 is 4 times 1 is 4. So we're going now to simplify the exponents. We have a to the power of 6 plus 3 is 9 minus 4 is 5. So therefore, we have a to the power of 5 over 12. Or this can be written now as the 12th root of a raised to 5. So this answer is in the simplest form because the exponent is smaller compared to the value of n, or the index. Okay, so if the exponents of the radicand is greater than the index, that's the time you are going to simplify it further, just like what I did for letter A. Now for letter C, I will solve that one on the other slide. So let us apply the properties of root for this. I guess that is now similar to number 3. So let's try. Okay. So to simplify that one, I'm going to, since the outermost radicand or outermost index is 3, is similar to the value of index here is also 3 in the denominator, so we can write that one as a single form. So therefore, I'm going to write here the bigger cube root of a squared times the fifth root of a squared times the square root of a all over a. Now, so this one, This one and this one can be simplified further. So therefore, I can write that one as the cube root of a, because a squared over a is a, times the fifth root of a squared times the square root of a. Now, this coefficient of a from this fifth root of a squared times square root of a, if I'm going to put that one inside, I am using this property of the square root. If I have a square root of b, then it becomes now a squared b. Okay? If I'm going to use a cube root of b from mixed radical to a pure radical, if I'm going to put this one inside, it becomes now a cube times b. And so on. If I have a times the fifth root of b, so I can write the fifth root of, so the fifth root of a raised to 5 b. So I'm going to use this idea for solving for this. So I'm going to put this one inside to that and applying this property. So we can write now the cube root of the fifth root of a raised to 5 times a squared times the square root of a. Now, combining this one, so it becomes now a raised to 7. So I can write now as the cube root of the fifth root of a raised to 7 times the square root of a can be written as a raised to 1 half. Now, applying the one of the properties, we can now multiply the indices here between 3 and 5. So I can write now the 15th root of a raised to 7 times a raised to 1 half. Now, I'm going to simplify the radicand. So we can write it here. So we have now the 15th root of applying the law of exponent. So we can write now a raised to 15 over 2. So this is now the 15th root of a raised to 15 over 2. We know that 15 here, or 15 over 2, 15 is the exponent and 2 is the index. So we have an index of 2. We also have the index of 15. So in other words, we can write here as the 15th root of a raised to 15, and then we have times 1 half. So since this is just a denominator, which is also an index, we multiply the two indices. We have 15 times 2. Or we could write now as 15 times 2 is 30. We have the 30th root of a raised to 15. Or that can be written now as a raised to 15 over 30. Or that is now a raised to 1 half. Or the answer now will be the square root of a. And that's the final answer. Okay, now let's move on to the next examples. So we have the fourth root of a raised to 5 minus the fourth root of 81a raised to 5 plus the fourth root of 16a raised to 9. So this is simpler compared to the previous example. So we have, to simplify, we have the fourth root of a raised to 4 times a minus the fourth root of 81 can be expressed as 3 raised to 4. 3 times 3 is 9. So times 3 it's 81. And then times a raised to 4 times a. Plus the fourth root of, what's the fourth root of 16? We have 2 times 2, 4 times 2, 8 times 2, 16. So we have 2 raised to 4 of a raised to 8 times a. So factors of a raised to 9 is a raised to 8 times a, because if you're going to multiply that one becomes a raised to 9, and we can have the perfect nth root of a raised to 8. Now, simplifying this after we factor the radicands, wherein one of the factors is a perfect nth root. So the fourth root of a raised to 4 is just a. So the remaining term there is the fourth root of a minus the fourth root of 3 to the fourth power is 3. And then we have the fourth root of a raised to 4 is a. So we still have a outside, or the coefficient. And then we have the remaining of the fourth root of a in the second term. Plus, what is now the fourth root of 2 raised to 4? So 4 divided by 4 is 1. So therefore we have 2. And then a raised to 8, the fourth root of a raised to 8. So divide the exponent. 8 divided by 4, we have 2, so therefore a squared, and the remaining term there is the fourth root of a. As you can see, the radicals and the indices are the same, so we can combine their coefficients. So we can write now as the quantity of a minus 3a plus 2a squared of the fourth root of a. Now, I will just rearrange this one and simplify a minus 3a. So I can write now 2a squared minus a minus 3a is 2a, quantity to that, and then the fourth root of a. Or you can simplify this further, wherein there is a common factor of 2a. So you can write now 2a times a minus 1 of fourth root of a. So either of the two answers are accepted. Next, we have to evaluate each expression and write the result in its simplest form. So what is the cube root of 128? Another way of writing the answer is that we are going to find the factors of the radicand, wherein one of the factors is a perfect nth root. Or, like what I have done on the previous example, or the last example, is that I write 81 in terms of exponential form. So that's the other way of writing. Instead of finding the factors of the radicand, wherein one of the factors is a perfect nth root. So let's try. So we have the cube root of 128, and 128 can be written in terms of exponential function as 2 raised to 7. So 128 can be written as 2 raised to 7. So I can write here now the cube root of 2 raised to 7 plus 4 times the cube root of 16. So 16 can be written as 2 raised to 4. 2 times 2, 4 times 2, 8 times 2, 16. So therefore, 2 raised to 4 plus 2 times the cube root of 54. There is no single factor for that. So we can write now 27 times 2. But 27 can be expressed in terms of exponential form of 3 to the third power. So I can write 3 to the third power, which is 27, times 2. That will give you 54. Okay? So we can now simplify further. If the exponent of the radicand is greater than the index, then there is a perfect nth root. So we have 7 of divided by 3. So there is, we are going to factor this one instead of dividing. So we have now the cube root of 2 raised to 6 times 2 to the first power. That's now 2 raised to 7 plus 4 times the cube root of 2 raised to 3 times 2 to the first power to become 2 to the fourth power plus 2 times the cube root of 3 to the third power is a whole number. So just write times 3 outside. Then we have the cube root of 2. So simplifying this one, so we can now 6 divided by 3 is 2, therefore becomes 2 squared And then the remaining term will be the cube root of 2 plus the cube root of 2 cube is just 2 because 3 divided by 3 is 1. So therefore 4 times 2 times the cube root of 2 plus, in this case, we just multiply 2 times 3 because the radical is already in the simplest form. So 2 times 3 is 6 times the cube root of 2. As you can see, the radicands and the indices are the same. So we can now combine their coefficients. But I will simplify this first. All right, we can write now 2 squared plus 4 times 2 is 8 plus 6 of the cube root of 2. So simplifying this further, we have 2 squared is 4 plus 8 plus 6. We have now the coefficients of 18. So a sum of this is 18, the cube root of 2. Okay? Then, what about the next example? We have the square root of 3 times the cube root of 9 times the fourth root of 27. So in this case, this is multiplication wherein the indices are different. So if the indices are different, then we are going to find a common index. So to solve for this, let us rewrite first in terms of fractional exponent. So the first, this factor is 3 raised to 1 half times we have now 9 can the cube root of 9 can be written as we have the cube root of 3 squared times the fourth root of 27 can be written as the fourth root of 3 to the 27 can be written as 3 to the third power. Or I can rewrite that one again as 3 raised to 1 half times 3 to the power of 2 thirds times 3 to the power of 3 fourths. Now, I have the same base or bases. Then, I will write in a single form. And then that is now 3. And then I'm going to find the LCD between the denominators of 2, 3, and 4, which is now 12. So 12 divided by 2 is 6 times 1 is 6 plus 12 divided by 3 is 4 times 2 is 8 plus 12 divided by 4 is 3 times 3 is 9. So we can write now as we have 6 plus 8 plus 9. We have 23. So we have 3 to the power of 23 over 12. Or this can be written as the 12th root of 3 to the power of 23. But the exponent here is greater than compared to the value of n or the index. So therefore, there is a perfect nth root for that. If I'm going to subtract 23 minus 12, so the remaining exponent is 11. So I can write here as we have the 12th root of 3 to the power of 12 times 3 to the power of 11, whose sum of the exponents will become 23. So 3 to the power of 12 is a perfect nth root. So therefore, we can write now 3 times the 12th root of 3 to the power of 11 because 11 is less than compared to the value of the index. So therefore, this is now the answer. So rationalize the denominator of each fraction. So we have 5 over the 7th root of 3 to the 4th power. So rationalizing the denominator, so I can write here 5 over the 7th root of 3 to the 4th power. So here, our exponent is 4, which is less than 7. So we need to add something that becomes a perfect nth root, which is now 7. So in this case, I need to add 3 to the 3rd power. because 3 to the 4th times 3 to the 3rd power will give you 3 to the 7th power. That is how to rationalize the denominator in this kind of given. So I will write, as I've said, I'm going to multiply here by the 7th root of 3 to the 3rd power over the 7th root of 3 to the 3rd power. So multiplying this numerator by numerator as well as denominator by denominator, so we can write now 5 times the 7th root of 3 to the 3rd power over, this is the same index, we have 7, and 3 to the 4th power times 3 to the 3rd power, whose product for that is 3 to the 7th power. And we know that this can be cancelled. That's why we have 5 times the 7th root of 3 to the 3rd power over 3. Okay, since the exponent here is 3, which is now less than to the value of n, now that is now in the simplest form. Or we can now write, or we can simplify now 3 to the 3rd power. By showing this one, we could tell right away that this radicand cannot be simplified further or has no perfect 7th root. Since the exponent is less than the value of n, so I can simplify 3 to the 3rd power. So this can be now 5 times the 7th root of 3 to the 3rd power is 27 over 3. So take note, you cannot divide 27 over 3 because 27 here is a radicand while 3 there is a whole number, which is now actually 1/3. Okay, so therefore this can be the answer. So either of the two is accepted. Okay, for letter B, we have 1 over the cube root of 2 minus 1. Take note, we cannot just multiply by its conjugate for this binomial because it is not a square root, but this is now in terms of cube or the cubic roots. So in that case, we are going to use the algebraic identities for the cube of sum or difference to rationalize the denominator. Now let's recall on the difference of two cubes. Since the sign here is minus, so let's recall this one. We have difference of two cubes. We have a cube minus b cube. So what's the factor of this? We have, take the roots first. We have a minus b times, we have the square of the first term, a squared, and then take the opposite sign. We have plus the product of the two roots. We have a, b, plus the square of the last term. So that is what we are going to apply for rationalizing this kind of given. Now we are going to rationalize. So we have 1 over the cube root of 2 minus 1. This can be rationalized by following this one. So we have the square of the first term. So what is our first term there? We have cube root of 2. And then what are we going to do with the first term? We are going to square. So squaring the first term. And this will be plus because of the sign minus. A conjugate of that will be plus the product of the two terms, which is now these roots, okay, which is now the cube root of 2 times 1 plus, this is the last term, the square of the last term is 1 all over. You just copy this one in our denominator. We have the cube root of 2 will be squared plus the cube root of 2 times 1 plus the square of the last term is 1. Okay, so we have now simplifying this one. Since it's only 1, so we can simplify this one. So the square of the cube root of 2 can be written as the cube of 2 squared is 4 plus cube root of 2 times 1 is just the cube root of 2 plus 1 all over. Now, the product of this will be equal to a cubed minus b cubed. So we are talking about this one. This is the cube root of 2 minus 1 is somewhat like a minus b. And this one is our a squared plus ab plus b squared. So in other words, the product of these two denominators here, it will be equal to the cube of the first term minus the cube of the last term, or shall we say the difference of two cubes. So shall I say we have to cube the first term, we have the cube root of 2, then raise to the third power minus the cube of the last term. We have 1 cube. So therefore, the numerator is already in the simplest form, so I'll copy this one. The cube root of 4 plus the cube root of 2 plus 1 all over. This one will be cancelled. The 3 here and that 1. So the remaining now is 2 minus 1 cube is 1. Or you can write here as 2 minus 1. So we have here 2 minus 1, or 2 minus 1 is just 1. So actually the answer now is just the cube root of 4 plus the cube root of 2 plus 1. That's the answer.